Now we're going to start a unit that we on linear models that's going to introduce a new hypothesis class. And for a non-trivial, a substantial chunk of the next few weeks, we'll be looking at different algorithms for training these sorts of linear models. Just as a checkpoint to make sure that we are all on the same page, we've seen the concept of supervised learning. The idea that instances are assigned labels by concepts and your learner exploring a hypothesis space to find a hypothesis that best approximates that concept. So label data goes into a learning algorithm. It produces a hypothesis. Sometimes I also call it a model. And this hypothesis is a device that can take new examples and make predictions on them. And our goal is always to do well on these new examples. Specifically, we've also seen a decision tree learning algorithm. In addition to that, we've also encountered a few general machine learning ideas. One important idea that pervades modern machine learning is the notion that instances can be represented as features in a high-dimensional vector space. Another important idea that is going to be a problem going ahead always is the problem of overfitting. Overfitting is the case where your learner accidentally finds a hypothesis that explains the training data better than it explains any future examples. Any questions about where we are? Today, we're going to look at something new. We'll look at linear models, and it's a new hypothesis class. Anytime you encounter a new class of functions, it's worth thinking about why is this class of functions interesting? What kinds of concepts does this hypothesis class express? So we'll look at what functions do linear classifiers express. To get started, we'll look at linear models in a bit of detail. We'll look at linear classifiers and linear regressors. The cool thing about these sorts of models is they have an intuitive geometric explanation. So we'll spend a bit of time on that. And then I'll talk about a little bit of notation because I want to make all our lives easier when we actually get to the algorithms. That notational simplification by itself may look annoying, but just bear with me there. And I'll talk about the various algorithms that we will encounter for learning linear classifiers. But I want to go back to something that I think I mentioned in the very first lecture, or maybe the second lecture. Is learning possible at all? If we are only given, in every instance of machine learning, we're given a small slice of the instance space, and we are asked to reconstruct a function that we do not have access to, that agrees with the mind of nature on exactly those instances for which we don't have labels. And if nature were adversarial, we could never do that. If nature were adversarial, every time we reconstruct a function by filling in one of those question marks, nature could say, oh, yeah, you're wrong. If nature were adversarial, nothing stops it from doing that. So the only way in which we get around that, the only way in which we could possibly learn anything is by restricting the hypothesis space, is by restricting the set of functions that our learner explores with the assumption that nature also does not have full freedom to choose whatever function it wants. A good part of machine learning is really design of such function spaces that are easy to explore, are good enough on many interesting natural concepts, and can be implemented efficiently. Something that we've seen one example of that, which is decision trees with depth limitations. Another example of that is linear functions, and that's what we're going to do look at today. to kind of motivate this, imagine that you have a task where you need to separate out these circles from these triangles. And this is all the training data you have. You have it's in 2 dimensions, right? It's a 2-dimensional data set, which is convenient because I can also put it on a screen. And our goal is to somehow separate out the circles from the triangles. And let's say that the only 2 options we have are curve A here or line B. And in all cases, when I draw a separator like that, essentially I'm saying one side of this curve or line is blue circles, the other side is red triangles. Now, my question to you is, which of these is better? Yes.
Line B is better.
There's 1 vote for line B. Anyone else? So there are a few. So let's do a show of hands. How many people say A? 1 person, 2, 3. Okay, let's just round it up to 10. And how many people say line B? A lot more. So one of the 10 people who said curve A, can you justify your answer?
Because on the left side of the curve, it's all blue, right? On the right side, it's all red. So it's 100% accuracy.
On the training data. Yes. Is that always a good thing? So can someone justify the other choice? Yes.
I think curve A was more prone to what we said, overfitting.
So the answer here, the answer here was that curve A might be more prone to overfitting. Let me give you a slightly more complicated way of thinking about it. Sure, here I told you that only these 2 are the only 2 options. But imagine that your learner was allowed to search among the space of all possible curves. Okay. Now let's say I have a red triangle here. And now I'm going to find curve C that separates out the pluses and the minuses. Sorry, the circles from the triangles. Perfect. But no, maybe that's not the right one because I also have a blue circle here. And now I need to do this again. No. Why am I having so much trouble here? Huh? Oh, yes, thank you. Whatever. You know what I'm doing, right? But you know what I'm doing, I hope. So if my learner has the ability to draw whatever curve it wants, it can always find a complicated curve that perfectly explains the data. And the problem with that is the more complicated your curve gets, the more likely it is to overfit. So a choice here is to say, I'm willing to make some errors on a few examples. Maybe this one here, and this one here, and this one here, and this one here. But because my line is simpler, I might generalize better. There's no guarantee we will, because maybe the curve A is the true concept. Maybe this curve represents a river, and one side is something, and the other side is something else. And what is the boundary between the red and the blue? Yeah, sure, the river is a natural boundary. But there is a sort of a simplifying assumption that we make when if we choose the line, in assuming that these things that are too close to the boundary or on the wrong side of the boundary are errors, and I'm willing to make those errors during training with the hope that it generalizes better during test time. It's an assumption. It's every hypothesis space choice is an assumption. You can also make the same assumption about regression. By the way, I would have picked the line over the curve there, because if I allow my learner to explore arbitrary curves, then I can fit any noise in the data. So here's another example. You can make a similar argument for regression. I have a collection of data points, and I can pick curve A that perfectly passes through all the points. So by the way, the way to interpret this picture is my instance space X is maybe a number, and the value here is the function value, which is the label. So this is the label. And I could have a curve that perfectly goes through the data, or a line that goes through one point, it seems. And often we end up picking the line simply because if we allow for curves that can, if we demand that our curve should go through every data point, no matter how many points we have, we can always find a high degree polynomial that fits the data perfectly. A high enough degree polynomial can fit any data perfectly, which means that you're not really you're not generalizing to what you, there's no guarantee that you'll generalize well. And the hope here is with the line, you're making fewer mistakes on an average on future examples. Just as a quick reminder, we've not talked about regression a lot. So I want to remind you, regression is about predicting real valued outputs, whereas classification is about predicting categories, plus and minus one, or spam and no spam, and so on. We'll first talk about linear classifiers. I'll give you an example. Suppose you have a task where, or suppose you have a factory that produces robot arms, and some arms tend to be defective, and you're going to measure, or you're going to decide whether they are defective or not by taking two simple measurements: the maximum distance the arm can reach, and the maximum angle that it can rotate. Let's call that the distance is d and the angle is a. And somehow you've come up with a decision rule that says if 2 times d plus 0.01 times a is more than 7, that arm is defective. Don't ask me how you came up with this number, these numbers. I can tell you how I came up with it, but they're not going to be useful. So now, but the cool thing is now, once you have such a rule, you can apply it on every robot arm that your factory manufactures. If a new arm shows up, then you can make these two measurements, apply this rule, and turns out if d is 3 and the angle a is 200 in degrees, I think, I'm not sure, then something is wrong here, right? It should be defective. Yeah, this, oh, I know why. Yeah, it doesn't really matter, but you know what, I hope you know what I'm saying here. If the threshold rule is met, then you classify one way. If the threshold rule is not met, you classify the other way. This is how prediction with linear classifiers work. What we have here is a linear classifier. I have a problem with two features called A and D. Every feature gets a weight assigned to it. In this case, the feature D gets the weight 2, and the feature A gets the weight 0.01. You take the weighted sum of the features and apply, compare that weighted sum to a threshold. In this case, the threshold is 7. And if it is more than the threshold, you label one way. And if it's less than the threshold, you label the other way. What we have here is an example of a linear classifier or a linear decision rule. It's a very simple idea. Every feature gets its own weight. Every feature gets multiplied with its weight. You add up the weighted feature values, and you check that sum against the threshold, and it's an inequality. Either it goes one way or the other, and so you get two labels. Let's generalize this a bit. Suppose you have D features. So you have D-dimensional feature vectors. I'm calling them X. X is a vector with, it's a vector of D numbers. Your label is we're working with a Boolean space, output space. We're working with binary classification. Your label is either a -1 or a +1. The device that we are trying to learn is something called a linear threshold unit. A linear threshold unit classifies the example X using a set of parameters that I'm going to call W. W is also a vector. So if X is a vector that looks like this, X1, X2 till XD, there are D of them. Your W is also a vector that looks like W1, W2, W. There are D of them. So every feature Xi is associated with its own weight, Wi. In addition, you also have another parameter called B. B is the threshold against which you compare. And the classification rule is simply actually the threshold is -B in this case. The classification rule is you take the dot product of W and X, which is nothing but the weighted sum of all the features. You multiply each feature with its own weight, Wi times Xi. You add them all up, you get a number. And then to that number, you add the number B. You still have a number. And you check if that number is positive or negative. The output is nothing but the sign of that number, of the resultant dot product plus the bias. The parameters W are called weights, and the real number B is called the bias. So this thing is B stands for bias. That also explains the name of a machine learning service or a machine learning helper service called weights and biases, weightsandbiases.com. In any case, so the decision rule looks like this. If W transpose X plus B is greater than or equal to 0, you predict +1. If it is less than 0, you predict -1. That's as simple as it gets. I say simple, but if you've not seen this before, this seems like a lot of notation. So ask me questions. Yes, you've asked a question before, so I'll come back to you. Yes.
Why does the bias exist in the context of the previous problem?
Why does the
or any problem?
in the context of the previous problem, notice that here I'm always comparing against 0. In the previous problem, I was comparing against the number 7. So really, in this case, the bias is -7. So I could have written this as 2D. So it's behaving like the negative of the threshold. That's what it is. There's also a geometric reason for this, which I'll come to in a minute. Yes, your question.
Firstly, can weights be negative values, or like, a WI value in this?
Yes.
total?
The weights can be any real numbers. It can be positive, it can be negative, it can be 0. And there's a neat way to think about it. If a certain weight is positive, that means that particular feature is positively correlated with the label being +1. If it is negative, then it's negatively correlated with +1 or positively correlated with -1. If it is 0, that feature is irrelevant.
Okay. And what does sign mean here?
Sign is simply the whether it's positive or negative. The plus or minus that's attached to that number.
Yeah.
Yes. The question is, how do we find W and B? And the answer is, we make that a learning problem. The goal of learning is to discover good W and B from data. Because other than W and B, there's nothing else that controls the behavior of a linear classifier. That's what the learner finds. It turns out that this linear classifier has a neat geometric interpretation. So I want to kind of spend a bit of time on that. And I'm going to illustrate that with a two-dimensional example. Imagine you have an instance space with two features, x1 and x2. So I can draw that as this plane on the screen. So I have x1 and x2. And imagine that I have a data set that looks like this. There are some examples that are pluses and some examples that are minuses. And my goal is to draw some sort of a separator between those two things. A linear classifier is nothing but this object here, the sign of a bias plus W1x1 plus W2x2. Every feature gets its own weight. So x1 gets a weight W1, x2 gets a weight W2, and there's a bias. And I often use the notation SGN because that's the mathematical term for the sine function. If you ever see that without, this is equivalent to SIGN. But notice let's forget the sine part. Let's only look at the insides here. Let's only look at this quantity there. In particular, let's look at what happens when that quantity becomes 0. So when B plus W1x1 plus W2x2 equals 0, what do you get? What is geometrically, what is this object here? This thing is a line. It's the equation of a line. So I could draw a line like this. W1x1 plus W2x2 plus B equals 0. And this line, if this, basically what this means is at any point on this line here, maybe this point here, there's a certain value of x1, there's a certain value of x2. And if you pick those values of x1 and x2 and plug it into that expression, you get the value 0. But if I move slightly on this side here to a different point, it's going to be non-zero. If I move to the other side, it's going to be non-zero, right? Because only the points on the line have 0. I can draw an arrow pointing towards one side to show that everything on that side has B plus W1x1 plus W2x2 greater than 0. So any point here will have W1x1 plus W2x2 plus B is positive. Any point on the other side is negative. I'm just picking a convention here. The arrow points to the positive side. It just so happens it's also the normal to the line if we care, but that's what it is. The arrow is actually parallel to this vector W1, W2, which is actually the normal vector, the perpendicular, going perpendicular from that line. Okay, but that's not, let's come back to this, the next point here. But in 2 dimensions, W1x1 plus W2x2 plus B equals 0 is a line. And when you draw a line in 2 dimensions, you can say one side is positive and the other side is negative. In 3 dimensions, what do you get? A surface, a plane, to be more precise. A plane. It's easy to visualize 3 dimensions. The room that we are in is a 3-dimensional room. The Earth, everything that we are in is 3-dimensional. And instances in the 3-dimensional space could be points in the space. And when I say that a plane in 3 dimensions, imagine this surface, a flat surface cutting across this room. And what we do with this sort of a decision rule is to say one side of the surface is positive and the other side of the surface is negative. That's like the mental image that is worth keeping in whenever you see linear classifiers. But notice that we don't care actually about the value of B plus W1x1 plus W2x2. We only care about the sign. Maybe this point here has the value of maybe 17, and this point here has the value of 300. As far as this line is concerned, both those points are equivalent. Yeah, sure, B plus W1x1 plus W2x2 is different for those 2 points, but it really does not matter. Both of them are positive, so they are equivalent. Similarly, this point here and any of these things, they may have different values of that quantity, but they are all negative. We only care about whether it's positive or negative. In 2 dimensions, you have a line. In 3 dimensions, you have a plane. In any higher dimension, you have something called a hyperplane. The general heuristic is if you want to go above 3 dimensions, you just slap on the word hyper. So you get hyperplane, hypersphere, hypercube, etc. And the most important thing here is hyperplanes, lines, planes, hyperplanes, all of them slice the space into 2 parts with a flat surface. And these 2 parts are called half spaces. And one of these half spaces is designated as positive, the other half space is designated as negative. Luckily, we also have 2 labels, positive and negative. So the half space that's positive gets the label plus, the half space that's negative gets the label minus. And that's the geometry of a linear classifier. Any questions? One thing that I know from personal experience is at this point, you might be trying to imagine a hyperspace or a hyperplane. If you do figure out how to do it, teach me. Because it's, it's non-trivial or possibly impossible. Maybe impossible. The joke is that if you want to imagine n-dimensional space or d-dimensional space, you first imagine d-1 dimensions and add 1 more. I really don't understand the joke, but apparently mathematicians love it. Yeah, anyway. Okay. So the next thing I want to do is simplify the notation a little bit, mostly to make sure that your code and your math does not have bugs in the future. It turns out that, I want to go back to that question about why do we need a bias term? Okay. So I'll come back to this also later, I believe, but I want to mention it already. Imagine that you have this, it's easy to explain this in 2 dimensions. The bias term behaves like, is the B, right? What would happen if your B was 0? We have a line that goes through the origin, right? Well, you know what I'm doing. Yeah. You have a line that goes through the origin. If you force the bias term to be 0, that means you are demanding that your learning algorithm only searches over all lines that go through the origin. And maybe if your data set looks like you have pluses here also, no line through the origin can separate the pluses and the minuses. That means you are, by forcing the bias term to be 0, you are making your hypothesis space impoverished. That's what's happening. Okay, I'm going to introduce a little bit of notational simplification that allows us to stop writing the bias term and treat it as just one more weight that we have to train. Because that's what it is. It's just one more weight. The prediction rule is the sign of W transpose X plus B. So this W transpose X looks like W1, W2, WD transpose X1 till XD. Now, imagine, so I hope that you know how dot products work. This is what basically you're taking a dot product between these 2 vectors, plus B. Now, the parameters that we want to learn are these W's and this B. So if I have a d-dimensional linear classifier, I'm learning d plus 1 parameters, right? The d weights and the 1 bias. Instead of thinking of it that way, imagine that I add 1 more feature. I move all of this down and all of this down. And I add 1 more feature, which is always equal to 1. If that's the case, if I do that and I put the B here, That means I get the exact same value. Because b gets multiplied with 1, the total sum here is b plus w1x1 plus w2x2 plus so on. So that means I have these d plus 1 numbers just seen as one collective weight vector, and I just have a single dot product that I need to learn. I have not done anything, all I've done is just move symbols around. So let me say this in a different way. I'm going to rewrite the instance space X. I'm going to add one more feature to the instance, which is just a constant 1. No matter what the example is, the feature value is the same. It's equal to 1. I'm going to call that new feature vector X prime. If X had d numbers, X prime has d plus 1 numbers, the last of which is always 1. I'm going to rewrite W as the whole list of numbers W and then adding the number B at the bottom. So it is all the numbers W, the D numbers W, plus the B as a single vector. I'm calling that W prime. Notice that W transpose X plus B is exactly the same as W prime transpose X prime. What I have done here is I have taken my d-dimensional feature vector X and moved it to d plus 1 dimensional space. And in the d plus 1 dimensional space, I have a new weight vector W prime that passes through the origin. And it turns out that all I need to do is if I have an algorithm that can learn that d plus 1 dimensional weight vector W prime, I have learned W and B together. I've done nothing really fancy here. All I have done is just move symbols around. But it turns out by doing that, you don't have to keep track of that B explicitly. Instead, you just add a feature call whose value is 1 to your data, and everything just works out for free. The prediction rule originally was W transpose X plus B and take the sign of that. Now it is W prime transpose X prime and take the sign of that. It increases the dimensionality by 1, but it reduces the amount of bookkeeping and reduces one line of code that invariably people forget to add. So it's mostly there as a debugging. This notational simplification is mostly there for debugging. And in the new space, the weights W prime go through the origin. What I have done here is just sort of a notational simplification to hide the bias term and instead fold the bias term into the weight vector, just so that I don't have to keep writing W dot X plus B every single time. I'll just write W dot X with the assumption that there's always a B hanging around. That way, I have fewer mistakes in my slides, you have fewer mistakes in your code, and nothing changes in the math. Questions? Yes.
The vector W prime goes through the origin.
Why does it go through the origin? Because remember, if you're in the D plus 1, let's make the dimensionalities clear here. If W was a D-dimensional vector and B is a real number, then W1 or W time and concatenated with B is a D plus 1 dimensional vector. Okay, so that's point number 1. The second thing to note is if you have a linear classifier where the separating where the bias term is 0, then the separating boundary, the decision boundary, goes through the origin. Now consider the D plus 1 dimensional space. In the D plus 1 dimensional space, my prediction rule is simply the sign of W prime transpose X prime. The separating hyperplane goes through the origin in the higher dimensional space because there could also be another bias term in that space and we are not adding that. It's equivalent to having a bias. Other questions? Now that you've seen linear classifiers, let me give you a list of different learning algorithms that we will use to learn these linear classifiers in many of the coming weeks. Shortly, we'll encounter an algorithm called perceptron. Perceptron is an error-driven learning algorithm that updates the hypothesis only if it makes a mistake on a new example. It turns out that it learns a linear classifier. And then sometime after that, we'll spend a bit of time on theory and then come back to learning algorithms, and we'll encounter an algorithm called support vector machine. It turns out that it trains a linear classifier by minimizing a certain error function, a certain notion of penalty for misclassification. We'll spend a fair amount of time on that. We may not actually spend time on naive Bayes classifier, but it turns out the naive Bayes classifier is also a linear classifier. In fact, it's a subset of all possible linear classifiers. And then after a while, we'll spend some time on Bayesian learning, and then we'll come to logistic regression. It turns out logistic regression also learns a linear classifier. These are all just different algorithms for learning a member of the same hypothesis space. And they make different commitments as to how to pick a good classifier. In all cases, no matter how learning works, the prediction rule is exactly the same. In all cases, you learn some weights and biases. And the prediction is simply, when a new example comes in, you take the dot product of the example with the weight, add the bias term, and if that is positive, you say plus, otherwise you say minus. We'll be spending a fair amount of time on all of these things, but not right now, because there are only 2 minutes left, and this is about a few weeks worth of material. On Thursday, we'll look at the expressiveness of linear classifiers. What kinds of Boolean functions do linear classifiers capture? And then we'll start looking at some algorithms. Don't forget your homework. If you have any questions, use Piazza, come to office hours, etc.